Today we'll take a look at proving that an inequality is true through the principle of mathematical induction. We've been asked to prove that 12 to the n is greater than 7 to the n plus 5 to the n. When tackling this problem, one approach is to move everything to one side and show that 12 to the n minus 7 to the n minus 5 to the n greater than 0 is true for all n greater than or equal to 2. Let's get into the proof. So onto the basis step. Here we will be using n is equal to 2. That is because our question gives us that the lowest possible integer is n equal to 2. Substituting this in, we get that 12 squared minus 7 squared minus 5 squared is equal to 70, which is positive. Our basis step is therefore complete. Now onto the inductive step. As always, assume the statement is true when n is some fixed positive integer k, which has to be greater than or equal to 2. This assumption allows us to write that 12 to the k is greater than 7 to the k plus 5 to the k. We will use this later. We now need to prove that our statement is true for n is equal to k plus 1. Therefore, we will show that 12 to the k plus 1 minus 7 to the k plus 1 minus 5 to the k plus 1 is greater than 0. Let's start with the left-hand side. (12 to the k plus 1 minus 7 to the k plus 1 minus 5 to the k plus 1, which, using our index laws, is equal to 12 times 12 to the k minus 7 to the k minus 5 to the k. The reason we want to do this is to get an expression that resembles our assumption. We know from our assumption that 12 to the k is greater than 7 to the k plus 5 to the k. We can then substitute this into the 12 to the k on the second line, which will give us our new expression that is of smaller value. Hence the inequality is formed. On the fourth line, we will just expand the factor and move the like terms next to each other. So the terms with 7 to the k are now adjacent, as are the terms with 5 to the k. We now take the difference of these like terms, which gives us 5 times 7 to the k plus 7 times 5 to the k. And clearly this is positive since we have the sum of two positive terms. We have therefore shown that our statement is true for n is equal to k plus 1. Therefore, through the principle of mathematical induction, we have shown that our statement S of n is true for all n greater than or equal to 2.